3.2 Refraction as the bending of light rays. Using the simulation, we consider how light changes its direction when it travels from one medium to another. Different mediums have a property called index of refraction, or more commonly known as refractive index. Air refractive index is actually 1, water has a higher value, and glass has the highest of them all. Okay, these dashed lines represent the normal between the first medium air and the second medium in this box here. In the first example, we have light going from air into this box is represented by air and out to air again. Since the same medium, there's no change in the direction of the laser light. When we change the medium inside the box to water, the light ray changes direction. It bends from air into water and back into air again. Okay, now once again we're going to change the refractive index to a higher one, that of glass, and we see that there's a more bending of light when it goes from air into glass and back to air again. Okay, so as shown by the earlier simulation, when the light goes from air into glass and back into air, it changes direction, and the amount of bending is determined by this property of medium called refractive index. And we define refractive index as a ratio of the speed of light in the vacuum to the speed of light in a medium. So we use a symbol N for the refractive index of the medium, C refractive index of the speed of light in vacuum, and V speed of light in a medium. The speed of light in vacuum is 3 times 10 to the power 8 meter per second. Light bends when it enters another medium. The reason is because the speed of light changes as it enters each medium. Different medium will have different speed of light. Light travels the fastest in vacuum. Hence, vacuum has the smallest possible refractive index. The smaller the refractive index, the higher the speed of light. Right, before we consider the ray diagrams again, we look at the common labels inside a ray diagram. First, of course, we have the normal, which is perpendicular to the boundary between the two medium. In this case, we are medium of lower n to medium of higher n. Then we have here incident ray coming in and the light ray going out, refracted ray. Then we label the angle of incidence, angle of refraction, theta 1 and theta 2 respectively. We may use a simulation like this to represent the bending of light that goes from one medium to another. When a ray of light travels from a medium of lower refractive index to a medium of higher refractive index, it bends towards the normal. When a ray of light travels from a medium of lower refractive index to a medium of higher refractive index, we can see that lower refractive index to the higher refractive index here. Okay, this light ray will bend towards the normal instead of going straight here. This is another example, starting from a refractive index of 1 to a medium of refractive index of 2. The light ray, instead of going straight, it bends towards the normal. Okay, so when the light travels from a vacuum into other medium, it bends towards the normal. What about the reverse direction? When light travels from a medium of higher refractive index to a medium of lower refractive index, it may bend away from the normal. Okay, I mentioned that it may also undergo another phenomenon called total internal reflection. Okay, for now, we look at this possibility of bending away from the normal. Using the simulation again, now we start with light in a medium of higher refractive index 1.5 to another medium of lower refractive index 1. Instead of the light ray going straight now, it bends away from the normal. Okay, we have another example. Light going from medium of refractive index 2 to n equal to 1.6. So instead of going straight, the light ray now will be here. It has bent away from the normal.